Ludovic is a researcher from ETH Zurich, doing some, geophysics computations, mainly on GPUs, also on Lumi, and he's going to talk about the scalability and the HPC readiness of Julia's AMD GPU stack. Take it away.
Yeah, well, thank you, Karsten, for offering the chance to give a glimpse in what we're doing with Julia on a HPC level. And well, here for the topic, I kind of decided to focus a bit on the latest development we are doing within a project, jointly between kind of ETH Zurich, the Julia Lab, the University in Mainz, and the University of Lausanne, where we're trying to get basically some large-scale AMD GPU code to run on Lumi supercomputer, which is like the third largest supercomputer in the world and like Europe's fastest supercomputer, but using some CFD codes that's entirely written in Julia. So maybe to give a brief overview about the kind of domain science or the domain of application is, so I'm kind of partially working at a glaciology lab here at ETH, and so we are interested in doing some ice flow modeling, particularly interested in kind of high resolution modeling, kind of full Stokes modeling, so to resolve the mechanics and the kind of thermomechanics and potentially also hydrothermomechanics, so multi-physics coupling, to resolve light flow over, for example, ice sheets such as Greenland. And so the map here that we see is kind of Greenland ice sheet with the color is the kind of the ice velocity, surface velocities, and obviously is fairly boring. So most of the ice sheet is, let's say, it doesn't move or is super stable. But there are like some region like here close to the coastlines where there's this dark blue and even some region where it's pinkish, which is like, these are called like ice streams. And although you may wonder why to bother with those, so although they're like very few compared to the area of the ice sheet, I guess roughly it's less than 10% of the ice sheet that flows at fast rates, but somehow the ice that's lost through these streams of fast flowing ice is about 90% of the ice that goes away from the ice sheet. So it's kind of very weird numbers. But the other thing to see is also that kind of in some of these regions, like here the ice flows at several kilometers per year, so it can go up to 1,000 kilometers per year, while in the middle of the ice sheet, nothing moves. So that's kind of a bit a challenging project that we're looking for, and we're trying to understand if, what would cause this kind of viscous instability, like that the fact that the ice would flow in these narrow channels and basically escapes the ice sheet. And to do so, to resolve some shear heating and thermomechanical localization, we need fairly high resolution just to be able to resolve the physical processes. And so we got a Euro HPC, like an extreme scale grant to actually try to resolve kind of ice flow over ice sheets that would be equivalent of resolving and doing some large scale run. We needed about 5 million GPU hours, and so we applied to these Euro HPC computers and targeting Lumi because it has this massive GPU partition. Yeah, so kind of to maybe give a bit more insights on why we do it. So that's kind of referring to these streams. So kind of this figure here, what you see is one, like zooming into one of these streams. So basically where it's orange, so the color is the flow speed. Here it's in meter per day. So basically in the center of these streams, ice flows at about 1 meter per day. And on these sides, kind of nothing moves, and like spatially, this kind of the whole snapshot is about 100 kilometers. So this what's called shear margin. So the region where you've transitioned from no flow to high speed flow, basically, it's like a couple of 100 meters. And if one takes the strain rate, so basically the derivative of the above field, one ends up with this bottom plane. So we see that basically there is this in this region of intense shear, and that's kind of thermo-hydromechanical processes that lead to this localization. And well, we want to better understand it. And this happens like on these margins, on the sides of these streams, but this also happens on the bottom. So there are like recent work that was shown that, I mean, for those of you that may have heard or may be a bit familiar with kind of Earth system models and ice flow models, like, well, a current way to parameterize the things. So, well, the obvious fact is that when running an ice flow model, usually the velocities that we get in the model don't match the observed velocities because, well, obviously there are some processes that are not included. And one common way of dealing with that is to say, well, there is some sliding at the base because, well, of this frictional heating, etc. But without resolving it. However, like this introduces some bias, and our project, we want actually to try to resolve it. So going from the upper panel rather to the lower panel, where actually, if we include this thermal feedback, we can get internal shear localization, which kind of makes this this white line is this cold to temperate transition zone. It acts as an internal shear zone, which makes the kind of sliding layer, but kind of not parameterized, but physically motivated. So that's a bit the challenge and the goals of our project. Yeah, so now, well, that's some nice goals, but then how we do it, kind of technically and numerically. So we're kind of working on implementing some full Stokes model that implement this thermomechanical coupling to, well, targets. So it's like finite differences, computations, and iterative methods, because we need to target these large distributed memory machines. And so there are like many challenges, but I guess some of the current challenges, like what solver you're using, and while current solvers, they are usually too much memory inefficient. And so we really need to go to iterative solvers. So we're working a bit on that to derive some very lightweight iterative solver for stencil-based operation that would perform well on GPUs. And the way, so the other bit different features from these ice studies is their geometry. And there we need also, since we have a regular Cartesian finite difference grid, so we kind of develop some or import some fancy features from computer graphics for implicit surface representation, so that kind of we can represent continuous functions based on level set and sign distance functions. And this is also fairly efficient because everything is continuous, and yeah, then we can work with variational formulation, have weights that are applied without having to make too much branching in the codes. So the results of our preliminary results, what we're looking at is like to solve this ice thermomechanically deforming ice in some either predefined or not streams, and to see like over time. So here, like the animation shows that over time the arrow would grow, which is the flow velocity, and at the end of towards the end of the simulation, there's this bottom layer that forms in bluish, which is regions where we contour this shear heating or strain heating starts to become important. And well, here one sees it a bit better. So basically, if we have topographic, like if the topography, the basal topography is not flat, then we get some we can have localization that occurs, and then this shear heating, this internal shear layer would start to connect with and form a decollement. So the way kind of we do it now technically or on computational side, so we have a big running project that's called GPU for Geo, which kind of tries to develop Julia-based tools targeting graphics processing units for the geoscience as a broad thing, so geophysics, geology, geodynamics, because at least in computational geophysics, there's no, well, therefore some very standard application, there are some communities, some flagship codes, but most of the research is done by, well, everyone trying to develop its own code to target a specific problem to solve. And there portability in a wide term starts to be very important and can be a very important player, such that, for example, I want to be able to prototype codes that I'm writing, but ideally I don't want them to have another code that would run in production, so kind of overcome this two-language barrier, for example. And also I want my code to run fast, so if I'm solving partial differential equation, I want it to run on GPU, and now, well, there's like more and more different GPU vendors that are around, and ideally I want a code that I don't have to rewrite each time I switch supercomputer or switch machine. And then there's also the portability in terms of performance. So I want scalability, technically, ideally from my laptop up to thousands of GPUs, and kind of some, well, maybe the cherry on the cake, like at some point once I have like forward solvers and models that I'm happy with, that are up and running, I may want to go into optimization and sensitivity analysis, because at the end, ideally, I want to constrain my model with some geophysical parameters that come from observation or from laboratory experiment or other type of input data. So the reason why we do it in Julia and why it's actually cool is that basically Julia, in a nutshell, encapsulate most of the things what's on that slide, including Lumi, since kind of just running vget or curl to download the latest x86 binaries, so it runs out of the box there. But kind of now for the little code, what's really is nice in Julia is this kind of backend abstraction, and I guess there was quite some effort done recently. So it's really one thing that the Julia GPU stack now tries to be really, there are different efforts to make this backend abstraction a thing, hide it into extension and other things, such that while you have a code that doesn't know anything about what type of GPU you're running on until the very end, where you can select, oh, I want to run it, for example, on AMD GPU or on CUDA. I want to change my precision, the number of dimension, and then technically or ideally, everything would be handled under the hood. And since Julia has this just ahead of time compilation, this performance, this kind of static code performance features that, well, we are interested to get like very good performance out of that exercise. And so, for example, what I show you here is just, well, it's actually a true Julia code that uses PartStencil, which is a package for abstract stencil operation that runs on like different backends, so AMD, GPU, CUDA for NVIDIA, and threads, multi-threading. And so it's just like as computing fluxes and updating, like solving a transient diffusion equation here. And that could be resumed in like 25 lines of codes. And that, that little code can run on like latest NVIDIA GPU. Or also like on Lumi, it runs on this MI250X GPUs. We are involved and working together with people from, well, the Julia lab and from AMD itself to kind of make sure that AMD GPU, so which is needed to run on AMD GPUs on Lumi, gives similar performance than or same performance than the C++ counterpart. So here are some benchmark for a memory copy kernel and diffusion kernel as function of number of grid points or problem size of basically AMD GPU kernel versus heap C++ counterpart. And so it's kind of, Julia is totally on that side, it's totally on par with heap, and kind of has the same, let's say, the same benefits and caveat of the rather the AMD software stack and lower level libraries that could get some enhancement, as maybe some of you kind of figured out as well. Well, and then we can scale out. So that was portability maybe between backend, but then we're also interested in portability in terms of scalability and to be able to scale out to now not only one GPU, but thousands of GPUs and there as well. So thanks to these very good meta programming capabilities of Julia and multiple dispatch. So we can also write some short tooling or efficient tooling here, implicit global grid, for example, that would make, implicit global grid decomposition very simple. So from the previous code, we only need to add kind of that we want actually now to init our local grid on a global grid, say that after our update of our kind of quantity that diffuses, we want to update some halo that can hide communication and do all the standard optimization. And then, finalize the process. So 4 function call, with even the hide communication here, makes this kind of a state-of-the-art Poisson solver that would have like 95 or 96% of parallel efficiency. And so that were results that we get, for example, running here a Poisson solver for benchmarking on Pitzdaint, which is a we have in Switzerland, and also on Lumi, and we scaled up to 2,500 GPUs respectively, and get like a Julia code that runs with a parallel efficiency of the order of like 5% drop from the total ideal, while actually solving the problem. And maybe compared to the fact that with GPUs using MPI is mostly to handle different GPUs, so we don't hit the issues that some other people may encounter with Julia at scale, where if you run like on many MPI ranks, you may have some potentially issues. But the fact that actually the local problem size per GPU is fairly big and there are not as many GPUs as you have cores in a supercomputer, like the number of MPI ranks is usually fairly low compared to CPU code, which makes like that the Julia running Julia out of the box somehow doesn't have any caveat, at least for now. And then we get, so that's on Lumi, so making some profiling, we can see that we can hide here MPI communication behind kernel computation, and there would be quite some safeguards still where it could be worse. So if the network latency would be slightly larger, it wouldn't impact that much either. And maybe to kind of wrap up, so some kind of cherry on the cake is that, as like following also up a bit on Mose's talk, is that, Julia kind of recently really gave a big push in these automatic differentiation capabilities, and the fact that Julia language itself is differentiable makes it really some kind of a killer feature of that language, because now imagine you can have a code that computes, there's some functions, and now it's like here we use enzyme because that's GPU compatible so we can retrieve vector Jacobian products out of, so we have a GPU kernel written in Julia, and we can kind of define some gradient function overloading, just pass some shadows and actually retrieve, store in these shadow variable cumulated gradient from running that function. And those are basically transposed vector Jacobian product that we can then use to make an iterative adjoint solve, for example. And then basically you don't have to write more code, right? So you have your forward solver and just passing the forward function, calling them in a reverse mode, basically accumulating and making an additional iterative solving strategy with those gradients. You can get the whole adjoint coupled solution for your system without having to program or derive nonlinear adjoints or whatever. And that's a very, very interesting thing for like nonlinear optimization problems, basically. And the good thing is that even on these adjoint or inverse and autodiff generated kernel, performance is good. So here I was looking at for a diffusion, making a adjoint solution of a nonlinear diffusion problem, basically kind of the time per iteration as function. So if you increase the problem size, and that's the time in second per iteration. And so the forward problem is slightly faster than the inverse, than calling the inverse problem per iteration. But it's kind of a factor. So if we look at the memory throughput, so it's kind of a factor, roughly 2, but that's kind of to compute a full vector Jacobian product with accumulation on the GPU by a kernel that's generated by the AD tool. So that's fairly cool. Yeah, so well, I guess I can wrap up like briefly. So yeah, I mean, there was quite some improvement in the Julia for HPC and the Julia at scale over the recent year. And well, now, well, there are definitely some very interesting paths to follow to get like, overcome this two-language barrier and like work on the portability on different level. That's kind of mostly it. So if you're curious, you can check out. We have a little, I guess there's a little website where we have the project where it's kind of about some, if you're curious, like about this stream, so the Lumi project, but also like some of these like the software that we're trying to work on to run at scale on GPUs for the geosciences. So, well, thank you for listening. And if you have any questions, I'm happy to answer.
All right. Thank you, Ludovic.